Welcome to G Fun Facts Online. Imagine walking on a beach, not on sand made of ground-up quartz, but on countless tiny pearly spheres. These are ooids, the Earth's mineral snowballs, and they are geological time capsules. Often no larger than a poppy seed, these humble egg stones hold the chemical signatures of long-lost oceans, helping us unlock the secrets of ancient climates, vanished worlds, and even vital economic resources. So, what exactly is an ooid? At its core, an ooid is a small, layered sedimentary grain, typically less than 2 millimeters in diameter. At its heart lies a nucleus, a tiny fragment of a shell, a grain of sand, or even a hardened fecal pellet. Wrapped around this core is the cortex, a series of concentric mineral layers, like the rings of a tree, that record the ooid's history. The vast majority of ooids are made of calcium carbonate. Modern ones in places like the Bahamas are made of a mineral called aragonite. In the ancient rock record, many are made of calcite, either because they formed in seas with different chemistry, or they were originally aragonite and later altered. But not all ooids are carbonate. Geologists have found ooids made of iron, phosphate, silica, and even table salt, each telling a unique story about the water in which it grew. The seemingly simple process of how these spheres form has been a subject of scientific debate for over a century. How do these mineral snowballs get their perfect shape? The classic explanation is a purely physical and chemical one, requiring what's called an ooid factory. You need 3 key ingredients. First, water that is supersaturated with minerals, like the warm tropical seas of today. Second, a supply of tiny particles to act as seeds. And third, persistent agitation. This is why ooids are hallmarks of high-energy environments like shallow tidal shoals, where waves and currents continuously roll the grains around, allowing mineral layers to coat the nucleus evenly, much like rolling a snowball to make it larger. In this view, an ooid's final size is a balance between the rate of chemical growth and the rate of physical abrasion from colliding with other grains. But this model struggles to explain one key observation: the significant amount of organic matter found trapped within the layers of ooids. This has led to the development of biologically influenced models, which argue that microbes play a crucial role. This process is called organomineralization. One way microbes help is passive. Many microorganisms secrete a sticky slime, known as extracellular polymeric substances, or EPS. This biofilm acts like organic glue, coating the ooid and attracting calcium ions from the seawater, creating a perfect template for mineral crystals to form. The other way is active. The metabolic activities of microbes can directly alter the chemistry around the ooid. For example, photosynthetic cyanobacteria consume dissolved carbon dioxide, which raises the local pH and triggers the precipitation of calcium carbonate. Today, the consensus is that both abiotic and biotic processes work together. One popular idea is the conveyor belt hypothesis. In this model, ooids spend time resting on the seafloor where they get colonized by microbial mats, allowing for slow, microbially assisted growth. Periodically, storms or strong currents pick them up and carry them to high-energy shoals, where they are rolled, abraded, and polished into their characteristic spherical shape before settling down again. While calcium carbonate ooids are the most common, the rock record preserves a fascinating variety of types, each a fingerprint of a specific ancient environment. The mineralogy of carbonate ooids, whether they form as aragonite or calcite, is a powerful tool for reconstructing ancient ocean chemistry. Earth's history has swung between long periods of aragonite seas and calcite seas. This fluctuation is controlled by the ratio of magnesium to calcium in seawater, which itself is driven by the rate of seafloor spreading at mid-ocean ridges. When seafloor spreading is slow, the ocean has a high magnesium to calcium ratio, and aragonite formation is favored. This is the state of our oceans today. When seafloor spreading is rapid, more magnesium is removed from seawater, the ratio drops, and calcite formation becomes dominant. The Jurassic and Cretaceous periods, for instance, were prominent calcite sea intervals. Geologists can read this history in the rocks. Ooids with a primary calcite structure point directly to a calcite sea, while ooids that show evidence of being originally aragonitic are a sign of an aragonite sea. Then there are the ferruginous, or iron, ooids. Found in rocks called ironstones, these striking rusty red or dark green spheres are made of iron-rich minerals like hematite. Their formation signals a dramatic departure from normal marine conditions and points to environments with an abundant supply of dissolved iron, something rare in today's oxygen-rich oceans. Their formation is often linked to periods of sea level rise where low oxygen conditions allowed iron to remain dissolved in shallow seas. Another important variety is the phosphatic ooid. These are a primary component of phosphorites, the rocks from which we derive most of the world's phosphate fertilizer. Their formation is tied to zones of oceanic upwelling, where cold, deep, nutrient-rich water rises to the surface. This fuels massive blooms of phytoplankton. As these organisms die and decay on the seafloor, they release large quantities of phosphate into the sediment, which then precipitates to form ooids. The presence of thick phosphorite deposits in the rock record points to ancient periods of intense oceanic upwelling and incredibly high biological productivity. Because ooids form under such specific conditions, their presence, composition, and structure are invaluable proxies for reconstructing past environments. The very existence of an oolitic limestone tells a geologist that the past environment was a warm, tropical, shallow water marine setting with high wave energy, much like the Bahamas today. By mapping the distribution of these rocks, we can reconstruct the geography of ancient coastlines. As sea level rises and falls, the ooid factory migrates with the shoreline, and the resulting layers of rock record these ancient cycles. A fantastic modern laboratory for studying ooids exists at the Great Salt Lake in Utah. It provides a vital analog for ooids formed in non-marine, hypersaline settings. Unlike the Bahamian ooids, those from the Great Salt Lake have a distinct radial fabric of aragonite crystals. Finding similar radial ooids in ancient limestones is a strong indicator of unusual water chemistry, like elevated salinity. This helps geologists interpret a much wider range of past environments. On the other side of the Atlantic, England's Jurassic coast is world-renowned for its cliffs of Mesozoic rocks, including famous oolitic limestones like Portland stone and Bath stone. These were formed during the Jurassic period, a time when Earth was in a calcite sea phase. The thick, repetitive layers of oolites here are a textbook example of how sedimentary sequences record the rise and fall of sea level in a world with a different ocean chemistry. Beyond their immense scientific value, ooids and the rocks they form have significant economic importance. Some of the world's most prolific oil and gas fields are found in oolitic limestones. This is because of their porosity. When ooids are deposited, they can form a grain-supported fabric, like a jar full of marbles, with significant pore space between them. If this space isn't filled by cement, it creates an excellent reservoir for trapping oil and gas. The Upper Jurassic Smackover Formation, deep beneath the U.S. Gulf Coast, is a prime example. Its oolitic layers are major hydrocarbon reservoirs. Interestingly, the brines within the Smackover are also the only commercial source of bromine in the U.S. and are now being explored as a potentially massive source of lithium, a critical component for batteries. Oolitic limestones are also prized building materials. Rocks like Indiana limestone, Bath stone, and Portland stone are all oolites. They are often freestones, meaning they have a uniform texture that allows them to be carved in any direction without splitting, making them ideal for detailed architecture. They are relatively easy to quarry, yet durable enough for centuries. This is why they were used to build some of the world's most famous structures, including Buckingham Palace, the British Museum, the Empire State Building, and the Pentagon. Finally, the same porosity that makes oolitic limestones good hydrocarbon reservoirs also allows them to be excellent aquifers, capable of holding and transmitting large quantities of groundwater. In England, for example, the Great Ooids Group is a principal aquifer, feeding numerous springs that are a vital source of water for local rivers. So from the sunlit waters of the Bahamas to the dark seafloor of the Jurassic, ooids are far more than simple grains of sand. They are dynamic recorders of Earth's history, each a self-contained archive of the water chemistry, physical energy, and microbial life of its time. By studying them, we can diagnose the health of ancient seas, track the grand tectonic rhythms of our planet, walk the shorelines of vanished continents, and tap into the energy and water resources that power our modern world. The OOID, in its perfect and humble sphericity, reminds us that the grandest stories of our planet's history are often written in the smallest of characters.